Welcome to the African Plants Georeferencing Trained Trainers Workshop. In this video, we introduce tools and documentation that can help during the georeferencing process. This video presents a general review of some of the many tools that are useful during georeferencing, but it does not delve into the technical details of each one or the integration with other tools. Also, we're not going to discuss geographic information systems. While there are several different georeferencing methods, we will focus on two of them in particular, the point radius and the shape or geometry methods. And therefore, we will explore tools that are relevant to the use of these methods. Just as a reminder, the point radius method provides a pair of coordinates and a distance, which is the radius of a circle, including all the location and its uncertainties. In this method, uncertainties are represented in a single dimension, the radial. The shape or geometry method, instead, provides one or more polygons, described by a series of consecutive points, points with buffers or polylines with buffers, so describing the extent of the location and its uncertainties in detail. To learn more about these methods, please refer to the corresponding publications cited on the screen and to the Georeferencing Methods class of this course. That said, there are numerous documents and tools that can help us in the georeferencing process, and a common question is, how do we choose one or another tool? In this video, we will present some of the tools available, mentioning their basic capabilities and shortcomings. All the tools that we will see are free, many of them are open, and have good documentation either from the source, from the community of users, or both. Also, we choose to show these tools because they are either more capable or comprehensive than many others available, and because they are easy to use and effective. We will organize this video keeping in mind the distinct processes involved in georeferencing, understanding these as a broad concept, including from data capture to data sharing. We will focus, however, in three key processes: interpretation and standardization of location data, and georeferencing itself. These processes will need of resources and actions that we will mention during this video. Interpretation and standardization of location data are essential to ensure a proper georeference. These processes involve location searching, visualization, and delimitation steps, and may also need data conversion and data cleaning. It is important to mention that these steps need to be performed conforming to current protocols and data standards. To learn more about standards, please refer to the corresponding class in this course. Starting with some tools that can help us to search for feature names, there are, on one hand, specific geographic gazetteers, such as the Getty Thesaurus of Geographic Names, and also more general sources of information, such as Wikipedia. The general sources have the advantage of being very diverse and may be a great sort of historical information. However, they present the disadvantage of usually being incomplete and inconsistent. For instance, the information that can be found in Wikipedia about some locations is different depending on the language we use to do the search. Also, different articles within the encyclopedia are more updated than others, and this can lead to errors. Let's think of an example where a country has changed its first-order administrative divisions, let's say dividing a province A into two new provinces, A and B. Due to this division, a department X that was in the original A province falls now in the B province. In the encyclopedia, the article about the provinces of the country may be up to date, hence showing there are now two provinces, A and B. But the articles of each of the different departments may not be up to date, and still show the Department X within the former Province A, which does not exist anymore. As you can see, depending on which article we read, we will end up concluding different things. This is a very simple example, but the problem extends to every level of locations. Gazetteers don't present this problem. They may be out of date, but they are consistent within. There are several gazetteers available, and it is always useful to look for national, regional, or local gazetteers where they exist, as they usually provide detailed information that can greatly help finding locations with their local, sometimes historical, names and in the local languages. We show here the Getty Thesaurus of Geographic Names, as it is one of the most comprehensive free gazetteers available. Getty works with a hierarchical system and provides identifiers for all locations. It displays the feature types for any given location and provides names in different languages, preferred names, and historical names. Search results can be obtained in different formats, and the gazetteer can also be accessed through an API. Here is an example of the results from the Getty Thesaurus for Gitega in Burundi, where we can see all the features mentioned before. In addition to searching for location names, we may want to find polygons that represent the boundaries of a given location and allow us to determine its extent. We can find such polygons, for example, in Google Maps, OpenStreetMap, and Google Earth. Google Maps has the advantage of offering several distinct views, including satellite and terrain, which can help better visualize the polygons in space. OpenStreetMap does not have a satellite view, but is still a very useful tool to find polygons and polylines. Google Earth, in turn, is poorer in this kind of information if not supplemented with external layers, but constitutes another suitable source. While probably being the easiest to use and having plenty of polygons available, Google Maps has the disadvantage that those polygons cannot be exported, and so are not usable in any other application. However, it remains a powerful tool to find locations and help determine their extent. We here show an example of a polygon encompassing the locality Gobabis in Namibia, found in Google Maps. On the left, we can see the map view, and on the right, the satellite view. The red dotted line represents the polygon. We have to be very careful, however, about how much we trust the polygons we find online. Here, on the left, we show the Google Maps polygon for the Gobabis town, and on the right, the polygon for the same town as retrieved from OpenStreetMap. As you can see, what is considered Gobabis is pretty different in both applications, and hence, so are the polygons that represent it. Deciding which one is correct can be a very difficult task, as we ignore the criteria used to delimit the locality in each case. For instance, one may be showing the Gobabis area, while the other may be strictly representing the densely populated area. These cases are more common than we think, and therefore we should always check that the polygon we're using fits the actual location we're trying to georeference, adjust if necessary, and always report the criteria used. Continuing with polygons, to apply the point radius and shape georeferencing methods, it is useful to be able to draw, save, and export shapes. This can surely be done using GIS programs like QuantumGIS, but that requires the user to be trained in this kind of applications. A much easier to use alternative, at least for these simple tasks, is Google Earth. As we can see on the screen, Google Earth allows us to draw any custom polygon and save it for future use. Also, it allows to draw and measure circles, which we can center on any given feature for which we have a polygon. This function is particularly useful when calculating radiuses needed to apply the point radius georeferencing method. Sometimes, and particularly if we want to check or complete the higher geography corresponding to a location, we may need to obtain the administrative divisions of different places. To obtain such layers, we can resort to repositories such as GATM or GeoBoundaries. GATM the database of global administrative areas, provides up to 5 levels of administrative divisions by country, showing both official names and variants, allows various output formats such as GeoPackages, shapefiles, R files, and KMZ, and provides table identifiers. In this screen, on the left, we can see how GeoBoundaries webpage looks like. This platform allows downloaded administrative divisions at different levels per country and has the advantage over GADAM that it can be accessed through an API. On the right of the screen, an example is shown of the download page in GADAM for Mali. Another useful feature we might need from this tool is the ability to draw paths and measure distances. To perform this task, Google Maps and Google Earth offer functions that are very easy to use. Google Maps, shown here in the upper left, allows manipulation of distinct segments of a path quite easily, providing lengths for each one. However, these paths cannot be saved for later use. On the other hand, Google Earth provides the total length of a given path, but allows saving, exporting, and reusing the polylines. Also, it provides an elevation profile associated with the path. Talking about elevation, although this data is often neglected, it is a very important piece of information for performing a correct georeference. To visualize elevation information, Google Maps offers a terrain view that displays the contour lines, from which one could infer the elevation range of a given location. Google Earth and other platforms, such as topographicmap.com, offer the possibility of obtaining the elevation at a given point without having to approximate with a range. Here we show the area of the Muhabura and Gahinga volcanoes on the border of Rwanda and Uganda on Google Maps using Terrain View. On Google Earth, with Terrain View enabled, notice that the elevation of a given place, yellow marker, is indicated below, and if you navigate with the cursor over the map, it will show the elevation corresponding to the points the cursor goes over. And the same volcano area as shown in topographicmap.com, where you can obtain elevation values by clicking anywhere on the map. As we mentioned earlier in this video, when interpreting and standardizing data to be able to georeference, we may need to convert values between different systems. This can help us find and delimit locations, integrating different sources of information, from the original textual description of a locality to data found in gazetteers, maps, and other tools. One of the most common conversions is that of coordinates between different formats. There are dozens of web pages that can complete this task. We only mention 3 here, and note that all are usually easy to use and mostly vary with respect to the input and output formats supported, and whether each set of coordinates must be converted individually or if batch conversion is available. EarthPoint, for example, supports both several formats, including grids, and permits batch conversion, which makes it a good choice to complete this task. Another useful conversion is that of coordinates between distinct coordinate reference systems or datums, of which there exist over 750 distinct ones. EPSG.io has a tool that allows transformation of coordinates between any given datums. Provided with the coordinates value in a given datum and indicating the datum to transform to, the web page will provide the new coordinates. Finally, within interpretation and standardization steps, we're going to mention tools that allow us to retrieve geographic information having only coordinates as the starting point. One such tool is Google Maps, where we can search for any given pair of coordinates, and placing a marker on the map, we can obtain the geographic data associated, such as the name of the country and region where that point falls. Another tool, InfoXY from SpeciesLink, is very easy to use and allows batch consulting and provides detailed information on the different administrative divisions to which the locations correspond, which can be downloaded as a table. Here, for example, we see the results of a search for 4 sets of coordinates in different African countries. And we can see in the results table at the bottom that for each one, the administrative divisions at different levels are provided. Now that we have seen several tools to aid interpretation and standardization of location data, we will focus on georeferencing itself, meant as the calculations that need to be performed to obtain the final values of the georeferencing parameters. This calculation will necessarily be affected by all the actions taken beforehand, including searching, delimitation, data cleaning, etc. First, we will mention a document that is fundamental for performing the georeferencing calculation following the point radius method. The Georeferencing Quick Reference Guide provides step-by-step explanations to georeference different types of localities, with graphical and real-case examples. This guide integrates the georeferencing best practices and the use of the georeferencing calculator. This calculator performs the georeferencing calculation in a simple way, as long as we provide it with values for the relevant parameters needed for georeferencing each type of locality. The calculator has an online version and a desktop version that can be downloaded, a detailed manual integrated with Georeferencing Quick Reference Guide, and its interface is available in 5 different languages. As mentioned before, the calculator works with the point radius georeferencing method and is supposed to be used having got familiar with the theory behind it, which is explained in the 3 documents that we cite here. The interface of the georeferencing calculator looks like this. And the first thing that we will need to be able to use it is to define the type of locality we're dealing with. The possibilities are coordinates only, geographic feature only, and different distance options shown on the screen. By choosing any of these types of localities, the calculator will display fields for the specific input parameters that we should provide to perform the calculation. We can, for example, choose the type of locality, distance along orthogonal directions. In this case, we will need to provide parameters for the coordinates, including source, format, precision, and datum. Also, we will need to specify the distances in given directions, their units and precision, the radial of the reference geographic feature, and the measurement error. With these parameters, we will obtain the georeference following the point radius method, which means we will have final coordinates with their precision and datum and a radius which represents the net uncertainty of the georeference, together with a series of georeferencing metadata. At the bottom, the calculator also offers a distance and scale converters, particularly useful when working with paper maps. We will see the use of the georeferencing calculator in detail during one of the classes of this course. Finally, one last tool that we will show in this video is GeoPick, a semi-automated georeferencing tool that also follows best practices and uses the point radius and shape georeferencing method. GeoPick produces outputs that follow the Darwin Core standard and hence can be easily integrated when sharing the data. The tool integrates OpenStreetMap and Google View's default, terrain, satellite, and hybrid. In this example, I have searched for Ganley in Central African Republic, manually drawn a polygon around it, and produced a minimum circle encompassing its extent. Following the georeference calculation, GeoPick provides the final coordinates and net uncertainty, and other georeference data and metadata ready to share under Darwin Core fields. GeoPick is a very powerful and efficient tool, and we will explore it in detail during a live class of the course. Before the end of this video, I would like to go back to the question we posed at the beginning. Provided that there are so many tools, which ones do we choose to aid georeferencing? As we have seen, every tool has advantages and disadvantages, and can be optimal for certain cases and useless for others. Therefore, the key is to be able to use a combination of tools based on a deep knowledge of the location data that we handle and the capabilities of each tool. This has been a promenade over some of the tools available that can help us georeference. We encourage you to try them, and of course to try others. As mentioned before, we will get into much more detail on the use of some of these tools in our following lessons. We hope that you have enjoyed this video, and thank you for watching.